outlook perspective, if you want, on this field of hydrodynamical simulation of galaxy formation, which is something that has been occupying me in the last couple of years. And in a nutshell, the goal that we have here is to augment basically these cosmological simulations of dark matter that we can do very well these days, that give us the cosmic web and lots of dark matter halos with internal substructure. But when we want to zoom into those structures, we also want to see the baryonic component, that is the galaxies inside of them. And as we all know, galaxies themselves are, of course, very complex objects. In these interstellar medium, there's a lot of messy astrophysics going on, regulating the formation of stars. We also have phenomena of galactic dynamics, creating things like spiral arms, bars, and regulating the interaction with other satellite systems. And all of this fundamentally would like to get out in this program of computational cosmology out of the initial conditions left behind by the Big Bang. So that's, of course, what we know and love and have observed in the CMB with exquisite precision, and gives us this strange universe filled with cold dark matter and cosmological constant. And for the rest of this talk, I will assume that as the standard cosmology. Of course, you can, it's also an interesting exercise to perturb this around this vanilla model, but I will not address this in this talk. Rather view this as a computational problem par excellence, where the initial conditions are perfectly well known. And then you have a bit of, a lot of astrophysics that you would like to evolve forward in time on some supercomputer and get out a complex galaxy like this one. So that is the simple idea of computational galaxy formation. And I would like to give you a little bit of a flavor of where we are in this field at the moment. Of course, what we can do very well is the dark matter component. This is an old image, now 10 years old, from the Millennium simulation. And or even 20 years ago, now NFW, Navarro, Frank, and White, published their famous Navarro, Frank, and White profile describing the mean radial runoff density of these collapsed structures. And really not much has happened there. This result still stands and has stood for the past 20 years with small corrections around it. So I think, it's fair to say that the dynamics of cold dark matter we have numerically under control with rather high precision these days. So that's kind of a solved problem. But the attempts to simulate hydrodynamical galaxy formation have encountered much more trouble. And just to illustrate this, I want to remind you of some of the historical failures of that in the past decade or so. And these are some old diagrams that illustrate this. One of the problems that has always troubled simulations are that the efficiency of radiative cooling is just so strong that any naive attempt to simulate galaxy formation hydrodynamically gives you a lot more stars than you want. This is, for example, an old comparison of a simulated cosmic star formation history compared to data. You see that you overshoot the data by a large factor. This has been described as the overcooling problem. Also, up to very recently, attempts to reproduce something like a galaxy luminosity function have typically badly failed. Predictions from simulations had typically very different shape. You look at this is, for example, from the GIMIC program of the Volker consortium. These luminosity functions do not look like the data at all. And generally, you have this very steep faint end coming from the large abundance of small dark matter halos. This is a problem that is still to this very day around, even though we have made a lot of progress. Also, what has been a problem was that the morphologies of galaxies could not really be predicted very well in these calculations. In particular, there was always a dearth of disk galaxies. And these shapes from a hydrodynamical simulations from now 8 years ago do not really look particularly pretty. And in particular, there are no dominant disk galaxies. And if you invested more numerical effort in trying to simulate individual galaxies, so-called zoom calculations, more accurately, this is from an old work again from Abetik. You got a disk, but you always got a dominant bulge as well. So simulating and forming disk galaxies, disk-dominated galaxies, was always a huge problem. Rotation curves here, for example, look crazy. They were shooting up to 400 or 500 kilometers a second in the center. Nothing like an observed galaxy at all. So apparently, even these simulations that have a weak disk component made a galaxy that is just dominated completely by a massive spheroid, unlike anything observed.
Is that the same problem? I mean, overcooling gives you more stars
Yes, you're right. These are intimately related. These two problems, indeed. Yeah. Likewise, also the size problem. This has been described as the angular momentum catastrophe, first introduced in this form by Steinmetz and Navarro. They show that the galaxies didn't lie on the Tully-Fisher relation. They were too small, systematically too small too. So really not really a good state of affairs about 10 years ago. But in in the beginning of sort of this century, this decade, I would say, things have suddenly changed. Here are results from 2011, 2012, where first disk galaxies, successful formations in cosmological context of galaxies that started to look a bit like a Milky Way system appeared in the literature. Here are some examples, and these first success stories were still forming disk galaxies that had a too strong bulge typically and were too massive overall, but they had promising shapes. And this has gotten rapidly better. So several groups have in the last years published disk galaxies that looked increasingly more realistic. You can put dust lanes on, and it gives very nice images which look closer and closer to observational constraints. And we also got our own progress is sort of in this early paper reflected here, where we also got in this Auriga project a couple of nice disk galaxies. So suddenly flat stellar systems with bulges that were significantly smaller. So what made that change? Yeah, that's exactly what I want to talk about now. So you wonder what was really the key factor, and that's sort of what I'm getting to now. So to maybe give away the primary answer is that all these groups have alluded to much stronger physical feedback processes that tame star formation and reduce it to roughly observed levels. Now, what this feedback physics now is, this is going to be part of the subject later on in the talk, but the principal answer is that everybody in this field went to the upper envelope of what's physically feasible and plausible. And we are having basically trying all really, really hard to maximize the impact of feedback process. So that's, I would argue, is the key reason. There are a few other ones. Of course, the improved numerical resolution that is available these days has played a role. Some people argue this is an important factor. I actually doubt this. I think it's a minor impact. And in fact, probably more important is that the numerical accuracy of the methods has been improved. There have been some serious defects discovered in older particle-based schemes in particular that have been rectified. And so these improved numerical methods have helped too. Now, the big grain of salt here is that the successes have been achieved with often radically different assumptions about the physical nature of these feedback processes. And the fact that they all come out roughly at the same place tells you that there's apparently some freedom involved in tuning these physical recipes, and that's indeed one of the significant limitations of also the current work that exists. We are not yet at a stage where everybody agrees what the critical physics ultimately is, and I will discuss this a little bit more later on. So before getting there, let me first say something about the numerical technique. So what we use ourselves is a method that we developed because of the problems that we encountered in the smooth particle hydrodynamics method, and we use an adaptive moving mesh. And here I just want to illustrate this for those who haven't seen this. Many might have. So this is a mesh-based technique that is illustrated here at very low resolution in this differentially shearing disk to show you kind of one key feature is here that you have a differentially shearing disk, but this dynamic mesh doesn't disrupt itself. That's because of a mathematical property here of these Voronoi cells. This is a Voronoi mesh which is created by a set of points that are rotating around here. And the cells are basically always the region of space that's closer to any given point, closer to any other point. And these Voronoi cells, when they shear apart, you see that the sides between two cells, they change area. And as they shear apart, the area between two cells shrinks to 0, and then you open a new neighboring area to another cell. And basically what this means is you have a continuous transformation of the geometry of this mesh, which is the novel feature of this method, which didn't exist in other attempts to come up with moving meshes. Now, why are these moving meshes interesting? In galaxy formation, you have, of course, you develop large density contrast as the gas flows into the center of galaxies, and with this technique, the mesh flows along with the matter, and you have a number of more technical advantages than, in particular, low advection errors and no preferred spatial direction, etc. Other than that, this is a so-called finite volume method, second order accuracy, more or less a standard mesh-based approach, but now formulated in this quasi-Lagrangian way. Now, using this method, we have then implemented in this repo code a set of basic galaxy formation physics. So this is besides gravity, ordinary hydrodynamics, and then you have cooling, radiative cooling terms for helium, hydrogen, and 9 chemical elements. You have standard stellar evolution and the production of these chemical elements in this sector. And we also have a model for black hole growth at the centers of galaxies and associated feedback effects. Now, we think these are very important, as you'll see, because the black hole activity is eventually responsible for making large galaxies red and dead and quenching their star formation. So that's, I'll come back to this point, but just to say that is sort of a standard no-frills galaxy formation model these days. With that, we have carried out some time ago now this illustrious project. This was a simulation attempt where we now applied this repo code, this moving mesh, with this galaxy formation physics description in a large volume hydrodynamical simulation. This was about 100 megaparsec physical side length and 106 megaparsec to be precise, and about 6 billion hydrodynamical cells, 6 billion dark matter particles, and 6 billion tracer particles. This was actually a project carried out in close collaboration with my colleagues at Harvard, in particular Lars Hörnquist, and also in Cambridge, Deborah, my former student, and some people at the Space Telescope Science Institute. Such a calculation this calculation was relatively expensive. About 19 million CPU hours were spent on it on 10,000 cores. This is about a wall clock time of about 2 months or so then, and a serial machine would be about 2,500 years, roughly. This is then what you get out of this calculation. Here's a zoom that illustrates this. We have the dark matter on large scales, the common cosmic web. But now these simulations have enough dynamic range that you can zoom into individual dark matter halos, visualize other properties. Here's, for example, the gas temperature field in between the galaxies. We can then also see the heavy elements produced by the stellar evolutionary processes and expelled by galactic winds into intergalactic space. And if you keep zooming in, you eventually see also the stellar components themselves. So these are now star particles formed in the calculation. And here's, for example, a large disk galaxy now showing up. And you see it's relatively blue. It has a lot of young stars. And it has properties not unlike the Milky Way galaxy. So this is now not just the dark matter simulation, as you see, but you have once you have this baryonic type of calculation, you can study a lot of effects, not only the galaxy morphology, but of course also the diffuse gas component. Here is, for example, cold neutral gas in this white component. It's the supply for the star forming phase. And you can also look at things not so easy to observe. Here's the gas velocity field. Here you see these bubbles actually in shock structures into intergalactic space when galactic outflows driven by winds and AGN are impinging on the IGM. Compared to this, the dark matter is actually fairly quiet place, I would say. The baryonic physics is much more complex. And one of the most gratifying results we got out of this was that we saw galaxy shapes that looked close to or resembled certainly the shapes we see in the real universe. And in fact, by judiciously placing images from the simulation on this diagram, you get something that sort of resembles Hubble's tuning fork diagram with two arms of these galaxies, barred ones and non-barred ones, and ellipticals, and you have a lot of irregular train wrecks as well. So basically, we get a morphological mix, not so different from what's observed, and this morphological mix changes as a function of stellar mass. Here is, for example, the fraction of early type versus late type galaxies as a function of stellar mass. And you recover the observed trend that for small stellar masses, you are predominantly seeing disk systems. These are the blue things. And for massive galaxies, you're turning to mostly spheroidal elliptical systems. So that is naturally recovered in these calculations. And I found this result in particular very encouraging. We also match approximately stellar luminosity functions, or rather stellar mass functions, at a variety of different epochs. This is illustrated here, but you see there are still substantial residual problems. For example, at most apparent, actually at redshift 0, here's the stellar mass function data as dots in black, and the simulation prediction is the solid line, and you see that the faint end is still overpredicted, and also at the massive end, there's a still overprediction of stellar mass. But in general, especially at higher redshift, it doesn't look so bad. And together with the sort of shapes of galaxies, you can then also play games and create virtual observations of this simulated universe, create a light cone of observation, observe the stars and this light cone, and compare it with something like the Hubble, Ultra Hubble Deep Field. And you can tell what's the real Hubble Deep Field, but probably not from a distance. When you come up, you see it clearly. But I think the next generation of simulations will likely produce even better images. So that shows you basically that across the light cone, these galaxy sizes and colors evolve roughly as we observe them, which is telling you essentially that you have a galaxy population that's forming and evolving close to what is actually observed. Now, after this sort of success story, let me rather go back to the things we don't really understand yet with these simulations. And let me start with the fundamental problem of what regulates star formation to begin with. And that is, in the interstellar medium, an old and difficult problem that can be maybe summarized, or the essential point, I'd say, is the fact that the star formation proceeds much more slowly than you would naively expect. You see this by comparing the gravitational freefall timescale of dense gas in this galaxy, which you would naively expect that this gas should fragment away on a freefall timescale, form stars on this freefall timescale. But the actual depletion timescale of the gas, which you get from the gas mass and the star formation rate, is about a factor of 100 smaller. And so this efficiency of star formation is just this famous few percent. So we have still, and that's a very interesting problem, and I know Yves Ostreiger, for example, is working hard on this, making a lot of progress on explaining why this is this 1%. Now, there's also the other problem, however, and namely that if you look at on a halo scale and you take the stellar mass per halo mass as a function of halo mass, and compare basically the expected abundance of dark matter halos from the n-body simulations of cold dark matter universe. We know this very well. If you observe galaxy luminosity function, you can do a ranked ordered matching and then predict sort of what should be the stellar mass per halo on average, so that you can accommodate the real galaxy population in the cold dark matter universe. And this gives you this, by now, pretty famous curve, where you see that the star formation efficiency is strongly modulated by halo mass. And it's strongest at 10 to the 12 solar masses. The Milky Way mass scale, that's interesting. And even here, however, it's relatively low. So only some small part of the universal baryon fraction make it to stars even here. But then, more interestingly, even towards smaller mass scales, the star formation efficiency is very rapidly declining. That's also towards larger scales. And so we think that the physics of supernovae or AGN and maybe other things induce this strongly scale-dependent behavior of the star formation efficiency, because gravity here over these scales is more or less scale-free. So we can only understand this with the astrophysics now of galaxy formation. But these two problems, why the one problem of the 1% efficiency of star formation in the interstellar medium, and the other problem why m star over m halo is so much smaller than the universal baryon fraction, I think they are basically distinct problems, and you can't expect by understanding this, you do not have yet understood this other problem, unfortunately. In fact, it's well-known in the galaxy formation community that basically the value of epsilon ff kind of drops out in feedback regulated scenarios for galaxy formation, because you're ultimately only determining the star formation rate through the gas inflow and outflow rates, and the balance of those doesn't really matter what this value ultimately is as far as the star formation rate is concerned. This is shown, for example, in this plot by Phil Hopkins, where the star formation rate in a galaxy is shown for radically different assumptions of this epsilon ff. If you invoke feedback models that self-regulate this, then this epsilon ff drops out. This is also the reason why we typically had hoped in galaxy formation that we don't have to understand star formation regulation at all if it drops out in this way. Rather, that's right. So in particular, the gas fraction is totally different in this case. You're right. They look different, and that in turn has other consequences about their morphology, etc. Right, and the thickness, etc. You're right. Yeah.
So when you adjust the simulations to fit and get all this luminosity function and mass function and so on that you showed compared with observations, you adjust the feedback parameters so they give you that agreement.
Yeah, that's basically correct. Yeah.
And if you change the feedback, the feedback is not coming from basic principles, so not black hole feedback. So you just adjust the parameters. If you adjust it to something different, that efficiency will either drop or rise.
You mean the efficiency of the epsilon ff? Yes. Yes, that's true. You can. The question is whether there's a unique solution for your given model. We have 3 parameters in the feedback prescription, empirical ones that are there's a certain range that's physically plausible, and we adjust it to as few observational constraints as possible. That's what. That's a loaded question. So you can. So I'd say there are formally there are a number of there are I don't know. I mean, there may be 10 or 12 parameters. However, about half of them is not varied at all in this optimization. You just set them to whatever. Whether you treat the IMF as a free parameter, yes or no, is a question, right? We usually don't play with this. We just set it to a value, right? And you could marginalize over this basically, but we just set it to a plausible value, and then we have at the end 3 or 4 things that we really change more or less freely and we do not search the parameter space systematically. This is we try a few choices like a coarse grid and then guess, and that's what we use for running, and then we burn the time. That's what we've done so far. But yeah, so for complete disclosure. But you can, of course, you have to always be careful what is a prediction and what is a post-diction of things that you put in. Right? Now let me just go through this list of potential feedback processes that regulate the star formation in the end, because that's, I think, where much of the interest of myself and also much of the community is concerned with, because we have a lot of debate on what is the critical physics that should be followed here. Of course, supernova explosions input energy momentum. That's fairly clear. Also, stellar winds do that. We have black hole activity, and in some observed systems, you clearly see that they influence the galaxy, but it's debated whether they do this also in smaller systems. Then the idea is that maybe radiation pressure on dust could help to accelerate winds. This is also contentious, this idea. Certainly radiation does photoheat gas, and this heating has an impact. In reionization, we expect a substantial impact, especially on small galaxies through photoheating. The radiation fields also modify the ionization balances, and so that can directly change the cooling rates of gas on galaxies. We have things like photoelectric heating in the ISM. We have cosmic rays, cosmic ray pressure. That's something that is increasingly looked at, and I will also talk a bit about this later. Then the magnetic fields have always been lurking in the dark, and now they start to be included. And here you might expect effects just from the plane magnetic pressure, but also more hideous effects from hydrodynamical instabilities together with magnetic fields. And then there are more exotic things like TV laser heating and lots of even more bizarre things. But I think this is sort of probably the main things that are discussed. And so I now want to show you some of the things we've done in this area, on first starting with magnetic fields. So we can add magnetic fields to our code. We have that has its own technical challenges to do this accurately. We have in the first generation done a cleaning method with a Powell scheme, and only recently also managed to have a constrained transport scheme. What I show you now is with the Powell scheme, the cleaning method. So with this we can simulate this galaxy. This is one excised out of a larger cosmological simulation, one that looks particularly pretty like a Milky Way galaxy. Here you see again stellar density, or the stars edge on and face on, gas density and the velocity field. And here you see also the wind coming off from this galaxy. And if you now look at the magnetic field, you see that calculation produced a magnetic field in this disk of a couple of microgauss. And this field is, here is the horizontal component, the vertical component is largely in the disk plane. It's mostly aligned in an azimuthal direction at this point. This is the pitch angle here, the dot product of the B field and the rotational velocity, or the current velocity of the gas. And you see you have a large domain here where the B field is roughly aligned with the rotation in this disk. This particular calculation started with a very tiny seed field of about 10 to the 19 Gauss or so in the box, and then you have an amplification of this field through small-scale turbulent dynamo and a galactic dynamo up to this strength of a few microgauss. Here is this shown at very high redshift. Here are calculations that start with different seed fields, and they independent of what you assume at the beginning. So this is the problem we have here in ideal MHD, which is assumed here that we have to start with something, otherwise there is no amplification. No amplification is possible, and typically we just by fiat we just put a tiny field into the initial conditions. And turns out it doesn't matter in which direction this points, so this is forgotten in the highly nonlinear regime of this amplified field. And also, provided you don't make it too small, you will always end up with roughly the same field strength, because this amplification process is self-limiting. It basically goes on until the magnetic fields become dynamically important, and that happens. This is a little bit cluttered here. These are different simulations of different disk galaxies, and they all reach about 6 microgauss or so of a typical field strength in this disk galaxy. Here you see this small amplification, slower amplification due to the differential rotation of the disk. This eventually also stops, and here this black line, for example, shows you what happens if you have a major merger. There's for a short period, mostly due to the compression of the gas and amplification here by a factor of 2, but then the field strength decays back to this couple of microgauss.
You called it dynamically important. I find that actually has an effect on the galaxies.
Yeah, it has. Basically, it become the pressure forces start to reach. So the magnetic pressure forces start to reach the thermal pressure forces. That's what I mean with dynamic important. At that point, they start to actually impact the gas flows, and that indeed is when the dynamo process stop here. And we also find that there's a tiny, this basically puffs up the disk a bit and slows down the star formation just a bit, but the effect is fairly small. So we don't see the techniques we're using here, which is actually still a sub-resolution treatment in this from the ISM phase. You don't see a big effect on the star formation itself and the ISM phase. It's just question whether the inflow is regulated, and that doesn't change much, at least not if you only include magnetic fields. And the magnetic, what's however interesting is that the magnetic field strength you get in these galaxies is of the observed size, and then it shows you that plausibly the observed field strengths are just the way they are, because that's really where the fields start to become dynamically of importance, and then they stop amplifying. This happens at these micro-Gauss level. And here's a comparison of some of the simulation results with observational profiles, and you see they lie very much in the same ballpark. That also is true for the vertical field direction. And yeah, they are based in equipartition, yes. So that's indeed the case in our, as you know, it's known in our own galaxy. We have roughly the same thermal pressure, some magnetic pressure and cosmic ray pressure. And for the magnetic field, this is then here also the case. So the fields can amplify from very tiny strengths through cosmic structure formation and small-scale dynamo processes to the observed strengths. And then there is, the nice things here is the initial field strength drops out. So the final result is independent of what you start with, and there's no free parameter here, at least, as far as the magnetic field modeling is concerned. No. No, all the reconnection is all numerical, basically at the resolution level. So there is no ohmic effects are explicitly included. This is basically all left to numerical dissipation. Well, this can happen, yeah. I mean, there's locally, you just at some level, you're at small scales, you're not properly resolving all the little flux loops anymore and so on, and then they're averaged together. So, yes, so that's part of the effect, yeah. So now what we've done recently is to simulate with improved resolution many Milky Way-sized galaxies. This is how they look like. We have a sample of 30 dark matter halos of about 10 to the 12 solar mass in a very small mass range, and wanted to see, what's the variety of galaxies you then form. This is how they look like. They look prettier than 10 years ago for sure. So we now have galaxies that have spiral arms, that have feature bars and warps and all the stuff you also see in the observed universe, and you can then start to be even starting galactic dynamical effects in these cosmologically consistently formed systems. So you basically nowadays you don't need to turn to toy simulations necessarily. They are always axisymmetric typically to study galactic dynamics, but things like radial migration or so stars you can start to look into directly in the cosmological context, which I think removes a lot of the uncertainty in some of these theoretical studies where you often have a lot of arbitrariness in the initial conditions. And at least here you have the advantage that all of these systems are coming out of the computer and more or less directly out of the cosmological initial conditions. Oh, that's a very complicated, not so easy to answer question. So it depends a lot on the specific merger history. So even though this shows is, I mean, this is just 8 systems here now out of 30, and there are also some spheroidal ones, I should say. These are now all disk systems, but they're not all disk. They're dominantly disk at this mass scale, but there are some others. And even though the final dark matter halo mass is always the same, the detailed formation paths of these objects can vary substantially. Also, it depends on when was the most recent major merger, depends on what is the spin of these objects, things like this, and for tidal arms, for example, they can be induced, of course, by flybys of satellites and so on. That is often the reason why, for example, strong patterns are formed. But there are also other more subtle effects, like there can be activity. Nuclear inflows can trigger a little bit of a blurb of the black hole in the center in our models that will slow down star formation, as you'll see in a minute. Okay, but first, let me show you just that the properties of these things roughly agree with observations. Here's, for example, the sizes of these disks, the scale length. These are largely exponential disks. They are okay in terms of data for the stellar mass, or this is basically the same information, a half stellar mass radii as a function of stellar mass. And this shows you that we now get systems that are basically disk-dominated. Here, the stars are decomposed in their orbital dynamics into the orbital eccentricity. And this is histogrammed here. And you basically, when you are at +1, you are a star on a perfectly circular orbit in the disk plane. And in this distribution, you see that there is around 0. There's this part that is basically dispersion supported. That these are the stars that we associate with the central spheroid or bulge. And we typically then measure basically by mirroring this left part of the diagram. You get this one way to estimate sort of what is maybe the mass of the spheroidal system, and you can then say the rest. This blue part here is your disk. And the disks are, there are basically no case where there's no bulge at all, but they are relatively small, and these disk-to-total ratios are consistent with many disk galaxies. Only extreme pure disks are still hard to get with our.
What's the number in square brackets under disk-to-total?
This is a different technique to. I think this was from Surface Bright, this profile fitting. So you can also make a Sausage and exponential profile to the light distribution.
So these are two ways of defining.
Yes, that's right. So this is sort of a kinematic way, and this is in square brackets. You see those are usually larger. So, and most observational disk-to-total constraints are usually based on this. So we argue that way that, okay, we actually get closer if you would use this method to what observed values will typically tell you. So I think it's ambiguous, of course, to some extent, especially for an observational image, what is really disk-to-bulge ratio, right?
So these comparisons, the disk, spheroid, and the size, mass relation, and so on, you have the feedback and you have the magnetic field.
Yeah.
How would it look? What's the main effect of the magnetic field from this type of?
Very small. So we now include this per default, but we have also done some simulation without the magnetic field. These results will hardly change. They hardly change. Okay, so in this particular modeling, the magnetic field effect is, but I show you when it will actually change. You need to enable another effect. So here is the blue cloud, basically. So these galaxies largely sit in the blue cloud. Here is this star formation sequence. The Milky Way is this green star. They kind of populate this region. This kind of shows you these are plausible Milky Way lookalikes, maybe a little bit big. Another thing is what you can look at, check the old conjecture that, in inside-out formation theories, fallen of stuff, you, for example, would expect that the disk sizes should correlate with the halo spin parameter. That is sort of the classic theoretical description of how a disk galaxy forms. And this is actually true. We've checked this here also for these results, that the disk sizes, they correlate with the halo spin parameter. And we've done this because there was some confusion in the recent literature where it was claimed in some results that this correlation wouldn't really be seen in successful disk formation simulations. We see it here, but actually, if you look closely, this is because some part of the literature, they looked at the disk-to-total mass ratio, correlated that with the halo spin. No, that doesn't look so good. So what you see here is that basically you can tell the disk size is very clearly set by the halo spin, and that is theoretically well motivated. But whether the disk is very massive relative to the bulge requires further parameters to know. For example, the formation history, of the thing. So I think that makes sense. What's interesting, though, is that when we look at the recent black hole growth we see in these galaxies, this is the black hole mass growth since redshift 1. You see that, and here's the disk size, that the galaxies that have grown their black hole a lot make small disks. That's interesting. So we interpret this that they have, apparently the black hole growth in its feedback has reduced the cooling and prevented the late time formation of an extended disk. So that is an interesting correlation that's predicted here. The simulations are, we follow philosophy where we try to see how well these results converge in terms of how robust are they when you change the numerical resolution. We call this a so-called strong convergence test. There are different philosophies in the field, so we don't change the these nuisance parameters that we have tuned when we change the resolution, rather just change the mass and spatial resolution and then want to see how simulations, what the outcomes are. And it turns out they are fairly robust, at least in quantities like the sizes of the disks and also the disk to total mass ratio. That doesn't change if you can change extremely by very large factors the numerical resolution. And also the disks, even the disk thickness is consistent. But there is a small drift in the total stellar mass when you go to higher resolution. So, but it's not large. It's about 20, 30%. Here, yes, that's actually I forgot what the dotted lines are now. These are scale heights of the stellar disk, but this I forgot actually what this plot was, what the dotted line was, whether it refers to the possibly gas even, or whether it was another method of defining that. Yeah, but the key, yeah. So yeah, I basically don't remember what the dotted lines are. Unfortunately, I'm sorry. This is the stellar. It refers to the stellar disk. So the levels here mean actually what's level 3 here is much higher resolution than level 5. And so there's no systematic trend necessarily between the different resolutions, except there's a little bit more thickness, lower resolution calculation, as you would expect numerically. These are images of the H1 gas we simulate, so you can also look at this, and they don't look crazy. They agree also in the surface density profile of the H1 mass. These are average profiles here. They lie in the observed range in terms of sizes as well. Here's a comparison of the H1 mass and the disk diameters. It's consistent with observations, but we are on the upper envelope of the observed gas fraction. So somehow we still have too much gas in these galaxies, and that's one of the challenges to understand where's all the gas gone. We still are in the upper envelope here, even though we blow out a lot into the halo. And that brings me to another topic, namely cosmic rays. So this is something we've started to play with recently. And I think cosmic rays are, of course, known to contribute to the pressure in the interstellar medium in our own galaxy. And recently, many groups start to look into them. It's an old topic, of course, again, because they are having properties that makes them attractive to understand potentially galactic winds and outflows. Now, these cosmic rays are produced at strong shocks. It's believed that at supernovae remnants, 10 to 30% of the energy release will initially appear in cosmic rays. And also strong structure formation shock waves will dissipate some of the energy in cosmic rays. That's a strong function of the Mach number. And then there are dissipation mechanisms. So once you have the non-thermal particle population, these relativistic particles, most of the energy is in the protons typically, then you can have Coulomb losses. Thermalizing this again, you can also have hadronic interactions creating pion cascades and gamma rays. Now, one reason why the cosmic rays are so interesting is that they are dissipation timescales. If you, for example, think about, does it take longer for the energy in cosmic rays to go away compared to thermal energy? And the answer is yes, it takes a lot longer. So the dissipation timescale is longer, which is already tantalizing because it tells you if I have an energy or if you have a pressure in cosmic rays, it potentially hangs around longer. It doesn't suffer from the overcooling as much as the thermal energy. So that is one first fact. But then you have also that the equation of state is a relativistic 4/3 gamma. That gives you interesting buoyancy effects. And furthermore, in particular, when you have a composite of ordinary gas and cosmic rays, move that to lower densities, it will mean that the thermal pressure decays away by adiabatic expansion faster than the cosmic ray pressure. So you will be quickly dominated by cosmic ray pressure if you're an outflowing composite, right? So that is why cosmic ray pressure might be important now for the dynamics. And also, if you have a given amount of energy in cosmic rays and thermalize it, dissipate it to thermal energy, you actually get basically back more pressure than you started out with, again, because of the different gammas. So these are some of the processes. But cosmic rays can be thought of only basically in the connection to the magnetic field, because, of course, they need to gyrate around the magnetic field, and through scattering off these magnetic field irregularities, they are coupled to the gas in the through that mediating this forces on the magnetic field. So we need to think about how to, what is the transport now of cosmic rays in a magnetized gas. And even if, you would in principle think, okay, they are mobile along the magnetic field line, that's true, and not mobile transversely. But even if you had the straight magnetic field line, there is something called magnetic streaming instability. The magnetic field basically will, or the cosmic ray streaming along the magnetic field will create its own irregularities on the magnetic field line on which they scatter. So that reduces their speed with which they can move along the field to order the Alfvén speed. That is, still a somewhat open plasma physical question, I think. I'm not an expert on this, but this is a very interesting problem still to understand precisely how this works. But in any case, it is expected that cosmic rays can eliminate pressure gradients in the cosmic ray rather rapidly along the field lines, but limited to something of order the Alfvén speed. Now, what we then have done is to start out with simulations that treat the cosmic rays in a simple two-fluid approximation. So you write down the hyperbolic system of governing magnetohydrodynamics and augment it with an equation governing the cosmic rays. So this is this cosmic ray energy density, which then gives you an additional pressure. The total pressure is then the thermal pressure, cosmic ray pressure, and the magnetic pressure. And there's a streaming term here, and there's an anisotropic diffusion term as well. So often, the transport is modeled effectively with a diffusion term, where you have an anisotropic diffusion, where the transport basically happens along the magnetic field direction. And so this is then sort of the energy evolution equation of the cosmic rays, which you have to evolve in addition, even in this extremely simple treatment where you have only, where you don't have any spectral representation yet of the cosmic rays. And then there are adiabatic terms of compression in the Alfvén frame of the cosmic ray fluid. There are cooling terms and production terms of cosmic rays. When you do combine dynamics of cosmic rays and ordinary fluid, you have, for example, changes in the shock structures that are quite interesting. You can have a production of cosmic rays now at shocks. This is also Fermi acceleration there. We include this, parameterize the acceleration efficiency of cosmic rays as a function of the Mach number. And that changes, for example, the speed of shocks. Once you have cosmic rays, you have a more compressible gas. And to take this into account in a cosmological simulation, you need to try to measure the Mach numbers on the fly. So we do this. Here's an example of a blast wave of a cosmic ray, of a supernova, sorry. Here's the shock zone identified with these white lines. And then we have a relatively accurate way to measure the Mach number across the shock. And this is then used to funnel some part of the dissipated energy not into the thermal reservoir but into the cosmic ray reservoir. In this way, we can produce the cosmic rays, and with this coupled solver, we then also have the modifications of the shock structures and their speeds, etc., in our code. This is the first step, of course, but one that's giving already very interesting results, as you'll see in a minute. You then also need anisotropic transport. So you have the magnetic field included. The cosmic rays are allowed to diffuse or stream along the magnetic field. Currently, we only do the diffusion. And the anisotropic diffusion is actually surprisingly difficult compared to ordinary diffusion. It took us a while to come up with a robust entropy-preserving scheme that works on an unstructured moving mesh. This is just a numerical test that essentially shows you that it gives the correct result. This is a diffusing ring where you have a circular magnetic field and initially some cosmic rays here in a little concentrated arrangement, and then with time they should only diffuse around the ring. Okay, and you can have an analytic solution for this problem. You can check whether your code does the right thing and converges to the correct solution. And it does, even though somewhat more slowly than we wished, but it does. And then finally, with all of this machinery, you can go back to this galaxy problem and see what happens now if you have MHD with cosmic rays. And there are some really exciting things actually happening. You suddenly get winds by themselves without putting them by hand. So here is a side view of the gas distribution in a disk galaxy, which you don't see. The stars are basically here on the edge on. And this is the z velocity field in 3 calculations. One done with just plain cosmic ray physics, but no anisotropic transport. This is on the right. What you basically get here is you get a few fountain flows, sort of Parker-like instabilities perhaps. Some gas rises and falls back after kiloparsecs or above the disk. But apart from this, there's infall on top and infall on the bottom. But once you have anisotropic or isotropic diffusion, this is shown in these 2 cases, you suddenly get this huge outflow on top of the disk and at the bottom. So these are outflow velocities of about 100 kilometers a second developing here. That happens because the cosmic rays basically diffuse ahead of the gas and develop a strong gradient in the halo, which drives this wind. And this is a very interesting coupled dynamics between the thermal gas and the cosmic ray gas, and leading to a formation of an outflow. Then there are also other interesting differences induced by this. If you, unfortunately, this is a bit small, this panel here, but here's, for example, the magnetic field. You see an interesting difference in the magnetic field evolution between the isotropic diffusion of cosmic rays and the anisotropic one. In the isotropic case, the magnetic field lags behind and it's much weaker than in the anisotropic case, and the no diffusion at all. The question is, why is the magnetic field suddenly weaker? Just because you change the transport process from anisotropic to isotropic, right? That's the only thing that differs here. And basically, the reason is somewhat subtle. So you in the isotropic diffusion, what you do is you modify the terms of the galactic dynamo equation in different ways. And here is sort of an axisymmetric dynamo equation without ohmic diffusion terms, which we neglect in our ideal MHD. And here we look at the individual terms, and the critical thing is only that here these terms here, for example, this is the radial and vertical gradient basically of the magnetic field is much shallower in the isotopic diffusion. So this is an incorrect model where you basically diffuse the cosmic rays more than you should, and you then make the gradients in the B field shallower, which in turn reduces the amplification of the magnetic field. So there are these very interesting coupled phenomena now, but we are very, very intrigued by them because it shows you that you actually need to treat these processes as realistically as possible to get a correct picture of how these galactic winds and outflows evolve. Here's another application of this on much smaller scales now. We just started to do this. This is basically a stratified disk simulation where you have a small box, just a kiloparsec across, which is meant to be a small piece of a galactic disk. The disk here is at the beginning, seen here side on, and somewhere up here and down there are outflow boundary conditions. And here on the left, basically there's a part of an interstellar medium which is created here, is very turbulent by the exploding supernova calculation, by the exploding supernova here. And they dump, in this left case, only thermal energy. Here, the supernovae also create cosmic rays. But you see that this looks fairly similar to this. The cosmic rays here now add a little bit of pressure, puff up this ISM phase somewhat, but do not really create by themselves, for example, a wind. To do that, you actually need to add the transport process of cosmic rays. You need to allow them to move relative to the thermal pressure, for example, through this anisotropic transport, anisotropic diffusion, and then you get this strong wind. Here on the right, you also see a strong wind, but a very different one. This is basically a ballistic outflow that occurs when you place the supernova randomly, not correlated with the dense gas, and that gives them a much higher efficiency. But you see now that actually the ISM is kind of destroyed here. It's very efficient, but the wind has very different properties in this case, and it's also driven in a very different way. So that's exciting and interesting, and it suggests that it will be very interesting to follow this up in the future and understand much more accurately, what's the influence really of cosmic rays in creating these outflows. But our initial results suggest that it's fairly important. So I'm almost out of time. Let me make a few remarks on on sort of the things we're working on, or the things I'm thinking about a lot. And what I find particularly fascinating about galaxy formation is that it appears that black holes are playing a prominent role, at least for massive galaxies. And that is basically an incredible problem in a sense, because these black holes are, of course, even though they are supermassive, they are really tiny, yet they are supposed to influence whole galaxies. Of course, energetically, it's well known that it seems not such a crazy idea. Or a quasar will, over an activity period, easily release 10 to the 16 ergs or so. That's worth 1 billion supernovae. So that's quite a healthy amount of energy. So, but the problem is, of course, how does this energy couple to the galaxy? Is it just leaving the nucleus and leave the galaxy unharmed or not? That's really, I think, much of the debate in the field. And we know, of course, also that integrated over cosmic time, black holes play an important role. The black hole mass density is about 1,000th of the stellar mass density. And if you assume that 10 to the 15 ergs are released by every supernova for about 100 solar mass formed, and 10% mass accretion, or 10% of the accreted rest mass energy is released as energy, then you find that these two numbers are of the same order. Within effective order unity is the amount of black hole energy that's released compared to the supernova energy. So energetically, black holes ought to be a big player. But I think it's a big debate still whether they are as important as we think. So in our illustrious simulation, I should say that there's no way that we get big red galaxies and clusters of galaxies without black hole feedback. We just have no other way at this point. We need to allude to black hole feedback. But understanding this is very hard. The other thing that is, I think, going to be a big topic in this field is finally moving on to radiation magnetohydrodynamical calculations. And these are very difficult to do. And aside from the computation cost, they are also very difficult questions relating to their accuracy. So different. Here's one example that I found very striking by Sean Davis and collaborators, where they compared flux-limited diffusion approximation, the radiation transfer, and the newly developed, more accurate variable Edding tensor scheme. And then they looked at the problem of basic radiation pressure acting on this gas from the bottom, from some sources. And here on the left is the flux-limited diffusion. Here on the right, the variable Edding tensor calculation. And the question here was essentially whether you can drive an outflow from this radiation pressure in this case. And the result is that, in one numerical scheme you can, and the other you can't. And so you get a qualitatively different outcome in this case, which is, of course, alarming. So that shows you that one has to think particularly hard in this area, which methods are accurate enough for the job at hand. And I think that will occupy parts of our field quite a bit in the near future. And then finally, I think, and that, in my opinion, is the biggest challenge, the biggest bottleneck for us at the moment, is we're, of course, dealing with a multi-scale, multi-physics problem of really gigantic proportions. And to form a galaxy, you have to include cosmological scales. You're talking about billions of light years. And these are, large modes of 100 megaparsec or so are necessary to capture the formation of large halos. Yet you want to look inside in systems like this galaxy, which is 1 million times smaller or so. And then the very center of such a system are then these supermassive black holes, which have accretion disks, maybe the size of the solar system, which are 1 million to 10 million times smaller still. So and that is really something that is not possible yet, to capture all of these scales in one gigantic calculation. And it's, in terms of adapting to the spatial resolution needed for this, we made a lot of progress, but there's also a large dynamic range in timescales coming with it, which is far harder to accommodate as well, and there are no good solutions for this at this moment. So let me summarize briefly. So I told you a lot about the progress we've made. So we make nice disk galaxies these days. They match a lot of properties, and there are countless papers written about how precisely they match certain things and which we don't match. That's all very interesting, but I think we still have a lot of open questions. We haven't fundamentally understood yet how feedback really regulates and what the physics is responsible for regulating star formation. And here are a bunch of the questions we would like to answer. And we also haven't really understood yet how black holes manage to influence galaxies at a fundamental level. We put this in a coarse way in our codes. We get very suggestive results with it, but I think it's still lacking anything about a proof that this is the right physics. And I think, however, that the prospect is quite bright, and I do believe that with improved numerical techniques, we can contribute a lot to answering these questions. Thanks a lot.